Okay, good morning everybody. Can you hear me? Is that working well with the microphone? Great. Okay, so I'm supposed to tell you something about protein crystallography. This is a lecture that at home I roughly give in one semester, and I used to compress this down to 2 hours, and this time Karsten made me compress it even more to 45 minutes. So I'll have the same problem that Sean had, and I'm probably going to be talking as fast as I can, maybe faster than I can think. So if you have any questions, just raise a hand and interrupt me. So Frank Nese pointed out yesterday that crystallography is the kind of technique that only gives you the geometric structure of a molecule and nothing more. That's correct in many ways. On the other hand, imagine we wouldn't have that, right? So I remember starting out in this in a time when it was still kind of a luxury to have a three-dimensional structure, and nowadays you feel extremely limited in what you can do if you don't have this as a starting point. And I put up some structures from bioinorganic systems, some that you already saw, just to point out that the one feature that we have in our system is that these are all non-standard conformations. We're not just looking at proteins or DNA, where we're basically selecting from a toolbox of 20 amino acids or 4 DNA bases, but everything that's really interesting about our systems is kind of non-standard. So the more closely we can see what's going on, the more we can learn about it. If that is an enzyme like RLMN from Amy's group here, where you really see that it's not only about a metal cluster, and you also heard that yesterday, but it's the whole three-dimensional arrangement of an active site that you need to understand in order to get anywhere with interpreting how this catalysis comes to pass. This is a structure of nickel-iron hydrogenase from Wolfgang Lubitz's group, where they actually visualized a hydride, a bridging hydride, at a resolution of 0.9 angstroms. And of course, this is the oxygen-evolving complex, nitrogenase, or other large structures that we have. Now, when I thought how to compress this whole thing in order to get all the information into these 45 minutes, let's see how far I get with that, I thought, I should be able to do that, but to make it a bit harder, why don't I include another topic that's a bit on every structural biologist's mind these days, and that is electron microscopy. Because what we really want to do, that's the basis of all this, is we just want to see something that's very small, right? That's microscopy. And if what we want to see is some little object, then what we do is we shine light in it. This light gets in some way diffracted by the object, and the diffracted beam then usually is collected by an imaging lens to give you an amplified version, an image of what you want to see. That's all we want to do, right? Just that our problem is that we want to see atoms, and in order to do that, we need to use light that is of a suitable wavelength, okay? And of course, that's going to be X-rays, and that's what I'm going to talk about. But you'll see there are some problems, and X-rays are not the only light we can use. We can also use electron beams, because they're also very nicely in the wavelength range that we need to see these kind of objects. And of course, electrons are charged particles, so you can build electromagnetic lenses for X-rays. So the obvious solution to this problem, if that is an atomic object, is a protein molecule, would be to use an electron microscope. They are around, and they are a bit of a hype these days. You might notice if ever you open Science or Nature magazine. And yes, in principle, that is possible. So if you look at the different length scales and what techniques you need to visualize objects in these different length scales, then on the range of tissues and cells, you have light microscopy. On the range of proteins and atoms, you have NMR and X-ray crystallography. And in between, of course, there is electron microscopy. And if we look at electron microscopy, nowadays what people are talking about is usually cryo-EM. And cryo-EM comes in two different flavors that are fundamentally different. One of them kind of bridges the gap to light microscopy, to histology, to looking at cellular structures, and that is called electron tomography, where you basically take slices through your object and reconstruct a three-dimensional structure from that. So that would be a link to cell biology, while on the other side, we have what's called single particle analysis, and that is what gives you atomic resolution information. Very briefly, looking at electron tomography, these are kind of old school electron micrographs that people were able to make years ago. They are stained in some way, and then you make very thin sections. You image these individual sections, and you create stacks out of these sections that allow for making a 3D reconstruction of this whole cellular environment. And then, of course, on a computer, you can color this accordingly to visualize membranes and cytoskeletal structures, mitochondria, vesicles, these kind of things, filaments. And of course, if you get better and better, you even start to be able to visualize protein complexes. So that's one thing. That's cellular architecture. That's not very much of function, if you ask me. So the other side of cryo-electron microscopy would be, how do you get to resolutions that are as high as possible? And the trick to that, that's where it becomes relevant for crystallography, and that's why I'm talking about that, is this. That's what's called single particle analysis. So the problem is, if you have an electron microscope, then you usually have something like 300,000 volts on that, and an electron beam with 300,000 volts hitting a single protein molecule is a bit this whole like Death Star versus X-Wing situation. So what you do is you need to do this very often. Everybody on the Death Star would agree. And then you try to see that all these are not the images you get from there. So the images you get from there basically just are a grayish pixely image with hardly any contrast. Then you go over those with a computer and you try to identify individual particles that are in the same orientation. And then they're called classes. You average all the individual observations in a class where the molecules have the same orientation, and then you generate class averages that represent different views of such an object. Okay? And you do this 10,000, 100,000 times, and then it was actually Joachim Frank, I get to him in a moment, who then in 95 published this reconstruction of the ribosome, large subunit, small subunit, which is a single particle reconstruction generated by methods like these. Okay? And that is where crystallographers, modest as we are, said, termed the coin like blobology. And we're getting that back now. So I tell you, because nowadays this same technique led to images of the ribosome that look like this. And that is what's called the resolution revolution. This is mainly due to new detector technologies, new microscope technologies. And this whole field is moving a lot. And that is really what I had on the first slide. That is atomic microscopy in the true sense that you just actually visualize an object. Okay, now the important part about this is you're not looking at one ribosome. Okay, you're looking at many class averages that each are an average of multiple observations of a ribosome in the same orientation. So electron microscopy, single particle analysis is an averaging technique. It's not a technique that allows you to see one single molecule. And the same is true for crystallography. So most of crystallography is just exactly the same as this, just that we can't really make an image, which sounds like a pretty big problem, but I'll get to that. Now this is an electron microscope. It's way more expensive, so it's way cooler than a diffractometer. And of course, you might have seen things like this. In Science 2015, this was going around, and then this is a wonderful headline. The revolution will not be crystallized. It was the method of the year in 2015, and of course this year it got the Nobel Prize for Jacques Dubouchet and Richard Henderson and Joachim Frank, who invented this single particle analysis methodology. And that is really what we did all the time. That is crystallization in the computer, because that's what the method really leads to. And of course the successes of the method are then structures up to 2.2 angstroms resolution. This is already 3 years old. It didn't get much further since, but a bit. And you get electron density maps that look worse than a crystallographic map at the same resolution, but that is actually because this is a real experimental map, while we are a bit cheating. I'll tell you about that. Large molecular assemblies that even involve some amount of dynamic, right, give you these maps. Or of course, and that might be rather relevant for application, at 2.3 angstroms resolution, people are saying, well, we can even see ligands binding, and this is where the pharmaceutical industry gets interested. Novartis has already invested in electron microscopes, so let's just buy 2 of the machines and see where this goes to. Can't do this in the university environment. But so the developments are actually quite impressive. However, one of the issues that is not going to be solved so far, and that is a big advantage of protein crystallography, is the aspect of resolution. So in crystallography, we are able to go to resolutions that are still way beyond what you can reach in electron microscopy, and they probably will remain like that for a while. So a 3 angstrom map is a pretty bad map in crystallography. No, and at 3 angstroms, for example, you see if the dashed lines are the positions of 2 atoms, you wouldn't resolve them individually. You would resolve them at 2 angstroms. No, that's a decent resolution for a crystallographic structure analysis, while at 1 angstrom resolution you get individual peaks for individual atoms. And the picture I showed you before from the Lubitz group was 0.8 angstroms, where you start even to see protons, which is not what you normally see. So in that sense, for understanding what's really going on, resolution is a key aspect. Okay, good. So let's do crystallography. Well, the problem about crystallography is, of course, if you do exactly the experiment that I described before with your crystal, you hit it with an X-ray beam, and then you put a lens, then you get that slight problem that there are no lenses for X-rays. So this is electromagnetic radiation. You do not have any imaging lenses for X-rays. All you get is this kind of a thing that's a diffraction image. So in essence, solving a structure by X-ray crystallography means you need to do what a lens does in a regular microscope in order to obtain an image. That's exactly that. Okay. Now, what do we have here? We have what we call a diffraction pattern. And this diffraction pattern in real life looks, for example, like this. So this is an actual protein diffraction pattern. And that is an image that represents your crystal and that's the important part, the contents of your crystal. And this is an image that changes if you move your crystal in the X-ray beam. So it's orientation dependent, because this, in fact, is a lattice of dots. That's a 3-dimensional lattice, and you only get a somewhat weird 2-dimensional slice through this 3-dimensional lattice. And we need to measure all these little black spots, and in the first crystal structures, they were actually measured by hand. In order to get all the data, we need to solve a structure. And actually, that's not even all the data I'll show you. Okay, so we need to count and measure black little dots. It's kind of the most exciting type of science you can do, but you don't have to do it by hand anymore. So, and what that then means is, of course, we get that. We get diffraction images, but what we want is 3-dimensional structures. And 3-dimensional structures, you're used to looking at them like this. This is the little structure that you're going to solve in our practicals. It's a ferredoxin. But this is a structural model. So this, again, is the interpretation of the actual experiment by a human or by a computer. The actual result of the experiment to get from here to here is this, and that's what we call an electron density map. So that's a map of the distribution of electrons in space. Why electrons? Because X-rays are diffracted by electrons. Okay, so solving a structure, getting to a 3-dimensional model means interpreting an electron density map, and that process is fundamentally different from the first step, which is actually transferring the diffraction image into an electron density map. This is what we call structure solution, and this up here would be model building. We need to keep in mind it is a model, and of course, if your electron density map has this kind of quality, it's not very difficult to build this kind of model. If you have lower resolution, it's harder. Electron microscopy has the same problem. If you have lower resolution, there is much more room for interpretation here. Okay. Now, crystallography needs crystals, obviously, and protein crystals, if you never saw any, may not look like what you expect. You have the idea that protein is something large and not very symmetrical. It has some odd shapes. Protein crystals are beautiful, if you ask me. That's kind of a personal opinion, but at least they look like crystals. So they have sharp edges, they have often uniform sizes, they have symmetrical shapes, although the actual molecules that build these crystals can be very, very asymmetric. Now, of course, if you have a cofactor, these are hemoglobin crystals, then the crystals also have the color of that cofactor. And one question would be, why do proteins crystallize in these very regular shapes? they weren't that regular, it wouldn't be crystals, but that's a moment. And the other thing is, why do they crystallize at all? Because obviously this is a more ordered structure than a protein in solution would have. So what drives the crystallization process? And the answer is, of course, crystallization only occurs if the free enthalpy of the entire process is negative. That's, thermodynamics, right? So at some point you need to release energy. And the point where you release energy is when individual protein molecules that are in free solution and are hydrated with a complex hydration shell are able to lose a part of that hydration shell because they get in touch with another protein molecule close by. And there can be some mutual equilibration of charges on the surface and whatever. So in essence, you will gain entropy by releasing water molecules that were forced into an ordered hydration shell. And that is what actually drives the process. And that means that in the beginning, when there are not too many protein molecules close together already, that can take a while. And that is a phase that we call nucleation. No? And in this nucleation phase, you form small clusters of protein, and then at some point, all of a sudden, this process reverses, and the initial cluster of protein molecules is large enough that any further growth will be energetically favored. And then they grow very fast. In practice, that means you make your crystallization drops, you look at them 5 minutes later, then you look at them an hour later, then you look at them half a day later, and a day, and a day, and a day, and you start to get really bored and you don't see anything happening. And then after a week, you go there and you find huge crystals that were not there the day before, because this and that are two different processes that can have very different kinetics. But the entire thing in basically all cases is energetically favored, so every protein in fact wants to crystallize. Not every protein knows that. You have to obey the laws of thermodynamics, and you just need to point that out, and you need to generate the right conditions, for which of course the concentration of all compounds are important: pH, ionic strength, temperature, dielectricity. It's a multi-dimensional space of variables that you have to basically thoroughly search. And we call these phases the nucleation phase and a growth phase, and again, they can be very different in their growth kinetics. And basically what you want is, you want ordered protein crystals where all the molecules look the same. That is our single particle averaging thing. We tell those molecules to stand in line before we actually shoot them with X-rays, rather than electron microscopy, where you just shoot and then you see who's lying around there. Texas style. Sorry apologize to all the Texans. Now the important thing about that is, and this is a picture I stole from Alan Darcy from Novartis, who talks about this wonderfully. Now if your sample consists of many different things that are, if it's impure, if it has many components, it's not likely to crystallize. If these things aggregate, it's not likely to crystallize. If you have flexible domains, it's not likely to crystallize. If you have flexible tails, it's not likely to crystallize. Cut them off. If you have proteolysis occurring, if you have partial unfolding, everything that introduces inhomogeneity makes it harder for those proteins to crystallize. Sometimes they still do, but basically your success in protein crystallization depends on your quality as a protein biochemist. It depends on the purity of your sample. So if you have pure protein, you're quite likely to get good crystals in the end. Okay, now what is a crystal? A crystal is a three-dimensional repetition of a smallest building block, and this smallest building block is called the unit cell. This unit cell has to be a geometric structure that completely fills space. It's only a crystal if it consists of building blocks that completely fill space. So this thing can be, well, it has to be a parallel epiped, which means that all these sides here are parallel, but it doesn't have to be a square. It can be a triangle, it can be a hexagon, it can be, can have any of different shapes. So these are possible shapes for unit cells, but it has to be able to fill space completely. And your task as a crystallographer is to understand the content of the unit cell. And in order to understand the content of the unit cell, you basically need to understand the architecture of your crystal first. And the architecture of a crystal is described by one of 230 so-called space groups of your crystal. So there is only 230 different possibilities how objects can arrange in different shapes of unit cells, plus, and that's important, plus internal symmetry in that unit cell, to give you arrangements that lead to a complete packing of space without any gaps. So your crystals must be, every single crystal must be part of one of these space groups. And if you do protein crystallography, it's even a bit easier because all your proteins are chiral molecules. So you can forget about all the space groups that have mirror planes or inversion centers as symmetry elements, because these would turn L amino acids into D amino acids, and that's obviously not easily happening in a protein. So we are left with 65 different space groups out of these 230, and they belong to all crystal classes. You might have heard about this. We don't need that much. And you basically need to build, to understand, to model the contents of your unit cell. And that's not precisely true, because within the unit cell, you can still have symmetry. And that symmetry you can take into account. And what you actually need to build is only the smallest part of the unit cell that does not contain any further symmetry elements. That's called the asymmetric unit, and you can visualize this nicely here. So this is a two-dimensional crystal, right? You managed to co-crystallize these birds with these flying fishes. Congratulations. And if you look at it, then quite obviously, the structure that you're after is a bird and a fish. So your structural model should be a bird and a fish. And if you take a bird and a fish, like that would be these two guys here, then that's what you want to know. However, if you take this one over here, you can put it here, you can put it here, you can put it down here, at all different positions in space. But you cannot put it here, because here the bird is looking up and the fish is looking down. So what's actually happening here? Well, that is symmetry. There is a twofold symmetry axis right here. And this picture is only up here, and down here is rotated around this symmetry axis. So there is an internal symmetry, and the actual unit cell of this crystal would be consisting of two birds and two fishes with the twofold symmetry axis in the middle. And still, your model that you're interested in is only the bird and the fish. So that's the difference between a unit cell that builds your crystal and the asymmetric unit, which is your task as a modeler to interpret. Okay, so that's what we're after. However, because this is a three-dimensional repetition in all directions, once we understand the contents of the asymmetric unit and we know the symmetry operations in the crystal, we can construct the entire crystal. So we know the position of every individual atom in the entire macroscopic object that is a crystal. Okay, good. Of course, that leaves the question, nice and good, but why do we need those crystals at all? I totally haven't said that yet. And the reason for that is that if you diffract X-rays on a crystal rather than on a single molecule, you will have a parallel wave of X-rays hitting this entire crystal lattice where all those molecules are nicely arranged in different rows, and the scattered waves that will emanate from these individual molecules then will interfere. And what you get is constructive interference and destructive interference. And you see, this is just a simulation of a little grid with just 4 grid lines and 8 grid lines. And if you look at diffraction on such a grid and the constructive interference and what comes out, then you see that what you get is diffraction maxima, interference maxima that are discrete. That's one thing. And of course, they are much higher in intensity than the wave emanated from just a single slit would be. So those crystals, in the very most important aspect of what we have about them, are amplifiers. They are very strong amplifiers of the diffraction. And of course, they lead to discretization, so we do not get diffraction at every point in space, but we get distinct maxima. And the reason for these distinct maxima is the architecture of the crystal in the form of a lattice. So constructive interference on a crystal is a way of amplifying our diffraction process, but that is also what introduces the averaging. Like single particle analysis, at this point, we only get constructive interferences from those parts of a molecule in a unit cell that look the same in every unit cell. Okay, so we average over all the unit cells. I can tell you I can draw you every atom in that crystal. Yes, that's true, but what I draw you in truth is only a copy of the image that we get for the asymmetric unit, because that is actually an average of the entire crystal. Averaging technique. Good. Now it was Max von Laue who came up in 1912, that was like 6 years after Röntgen discovered X-rays. With this, he went to the Kaiser Wilhelm Society, which now is the Max Planck Society. That is why Frank's Institute yesterday still had the Kaiser Wilhelm Platz as an address. I was very impressed with that. Guy's not too popular in our place anymore, but anyway. And he presented that. So he shot X-rays at a piece of zinc blende, which is zinc sulfide, and showed the people basically that there is this kind of a diffraction image. And they were smart people, so they immediately understood that this diffraction image, of course, in some way must reflect the internal structure of the object where this diffraction took place. So the diffraction of the X-rays encodes the structure of the object in these X-rays, like you know from a prism or something. Right? It's basically, here it's just the, well, let's say the optical density that then leads to a differential diffraction of different wavelengths in a prism. No? And the information about the substance that builds this prism is basically encoded in the distribution, in the spread of the energies, the different energies of the white light that you put in. No? So we have an encoding of the structure in that object, and the actual process that happens is a Fourier transform. And that means that we have a real space representation of our structure. Now, this is exactly what a lens does. The lens does this Fourier transform. We have a real space representation of our structure, and we turn this into, let's just call it a Fourier space representation. And the trick about the Fourier transform is that it works both ways. So all the information that you have in your original object becomes encoded in this Fourier representation. And if you do it well, you can do the back transform. And what we get out of this Fourier representation, that's our little black dots. Now that's a diffraction image. And in this diffraction image, we have some features. The most important feature, obviously, are the black dots. And you now know these are maxima of constructive interference of the X-ray on the actual grid, which means you have a very high intensity, very much localized in a spot, and you just have background. You pretty much have nothing in between. One of these things is you turn the continuous information of a structure in space into a discrete information in Fourier space somewhere. You don't have information at every point here, only where the maxima are. Okay. Then the issue of resolution. Crystallographers can look at a picture at this and all of a sudden get totally happy, and you stand there and you're like, okay, great. And that's what makes us happy, is if these reflections extend very much to the edge of the plate, because the further you get away from the middle, the higher the resolution is that these reflections correspond to. So a good diffraction image goes far out to the edge of the plate. Then in the middle, you saw Max von Laue had a black spot. That was where the X-ray hit that thing. Our X-rays are a bit stronger nowadays, so we need to put a little piece of lead, a beam stop, that keeps the primary beam from actually hitting the detector, because otherwise everything would be black. That's why they all have a little white spot in the middle, which is a bit of a pity, because that is also, of course, where one reflection would go, forward scattering. That is the strongest reflection that we have in there and that we cannot collect for that reason. And the other thing is you have these funny round shapes here, loons we call them. And that is, of course, then something we might get into, where these loons actually come from. Okay. Well, in the middle, that's the beam stop shadow. Right. So what we do is we rotate the crystal. And if we rotate the crystal, and you can do that in the practical, not rotate the crystal, but go through the diffraction images. You can also rotate the crystal, but it's kind of boring. then you see that the diffraction image changes. So you rotate the crystal while you hit it with X-rays, and these little point patterns, they change. So we need to collect data at many different orientations to get different spots, to get different patterns. And then we need to assign all these patterns a numbering scheme, and because this is a three-dimensional lattice, we call that the reciprocal lattice, we need to find a numbering scheme how to place all these little reflections in space. And these are the so-called Miller indices, HKL. And that's just basically a scheme to say, well, we have a reflection, and we put this into a three-dimensional box that just has numbers 1, 2, 3, 4, 5, 6, 7 in each direction. And 0, 0, 0, that's the forward scattering here in the middle. That's a box that always stays empty, but that is the origin of the reciprocal lattice. Okay? And if we do this right, then we will have our data sorted in exactly the way that we need to put it into the formula for the Fourier transform. So there is two parts of information in each reflection. One of them is where is the reflection, the position of a reflection, and that exclusively depends on the geometry of the unit cell. If you have two completely different molecules that happen to crystallize in the same space group with a unit cell of the same size, they will produce the identical diffraction pattern. It's just the dimensions of the unit cell. The second aspect is the actual intensity of these maxima, and that is what encodes the contents of the unit cell. So what we really need to measure is the intensity of those unit cells. Okay. Quick excursus. Why do you call this reflections? Right? You imagine that a reflection is something that gets reflected somewhere, and that doesn't seem to be what's happening, because what we have is diffraction. Now, von Laue already introduced a very nice concept, which is the concept of lattice planes. If you look at a crystal lattice like that, let's just let it be a diamond, whatever, anything, then obviously you see that in certain orientations, the atoms that build this crystal line up into something that is a plane. If you live in a wine region like we do, you also know pictures like that. You pass by the wine fields in winter when the plants are not down, and you look into it and you see here these little sticks line up, here the sticks line up. So in these lattices you can imagine planes. That is just atoms in a row. These planes don't exist. However, if you treat them as if they would exist, you get some very favorable things you can do with them. The way you construct these planes is you take your lattice, let it be your vineyard, whatever, and you have a unit cell here. And then you just say, well, in which ways can I put lines through this? Many different ways, like this. And then the question is, of course, well, this is a set of lattice planes. How would I call this? Well, let's call it by the number of sections of the unit cell that this number of plates here generates. So number of planes generates. This is a parallel set of planes. It contains all the atoms that make the crystal lattice, and we would call this the 1 minus 1 plane. Because it goes up on A, it goes down on B, that's the plus and the minus, and 1 because it cuts the sides of the unit cell into one piece. This one cuts the A side of the unit cell into two pieces, this one into one piece, so this would be the 2-1 plane. Okay? That one is 2 and 3. That's the 2-3 plane. Okay? These are these lattice planes. What am I talking about? Well, what I'm talking about is that if you do this, you can think, for whatever reason, that maybe there is no diffraction taking place. Call it alternative fact. But maybe the X-ray goes in and is just reflected by this set of lattice planes. They don't exist, but, doesn't matter. So, what happens then? Well, what happens is, imagine you have a set of lattice planes and you think, no, I'm not talking about the atoms anymore. We're only talking about the lattice planes, and yes, they don't exist. Okay. you have a set of X-rays that get reflected on these lattice planes. Let's zoom in a bit. That's just two of them. Now, what you get is one beam here and one there. They come in parallel, they go out parallel, but this guy has a bit of a longer way than here. How much longer? Well, that's easy. This is an angle theta that this comes in. It's a reflection, so the angle theta is here again. And if you remember your good old trigonometry, then you will find that the same angle shows up here. Okay, and now you can actually calculate this length rather easily if you know the distance of your lattice planes. That's the path length difference between the upper and the lower X-ray. And that really is just, well, the sign of this is that guy, x half divided by d. Okay? That's this. Okay? Or the path length difference is 2d sine theta. Okay? And you will get constructive interference if that path length difference is an integer multiple of the wavelength. Simple enough. No? X equals n lambda. You put these together, that is Bragg's law, and that is what got them a Nobel Prize. These are the Braggs. So you see how easy it is to get a Nobel Prize in crystallography. You should really try it. Okay? Bragg's law is acting as if there were lattice planes, although there are no lattice planes. And this is what we use, and that works perfectly well, to completely predict where on a diffraction image you would expect a certain spot that belongs to a certain Miller index, to a certain HKL value. This is what we use to sort the reflections into this reciprocal lattice in the right way for the Fourier transform afterwards. And there is this very nice construction by Paul Ewald, the so-called Ewald sphere, which I will draw as an Ewald circle in 2 dimensions, that maybe helps you understand. Probably not, but you can look at the video later on. And then, anyway, how these diffraction patterns come to pass. And the idea is you have your crystal. You shoot an X-ray at a crystal, and that X-ray gets diffracted. And now what Ewald said is, okay, you know, that's what happens. Okay, but let's imagine all this is surrounded by a sphere, and this sphere has a radius of 1 over lambda. Now that's obviously not real space anymore. That's reciprocal space, 1 over lambda. So it's kind of a thought model. And we put the origin of the reciprocal lattice here, and then we say every diffraction maximum that fulfills Bragg's law will be on the surface of this sphere, because if you think about it, Bragg's law says we have a reflection on lattice planes that are here. That means that basically this is the angle theta, and this, the whole thing, is the angle 2 theta. And then, actually, and I'll just skip over this a bit quickly, but this here will then be 1 over d, which is the distance of the actual lattice planes here in the reciprocal lattice. And if you put that into Bragg's law, you basically figure out that Bragg's law is fulfilled if this distance fits in here, if this is 1 over d, and that is only the case on the surface of this sphere or on this circle in the 2-dimensional picture here. So only if a reciprocal lattice point falls on this Ewald sphere, you will get constructive interference. And that means that if you have your reciprocal lattice, out of all the reflections in the reciprocal lattice, only those will be on the Ewald sphere. And those are the ones that you will see on a diffraction image. And that's why it has this funny shape. That's why you have these lunes and these round things on the diffraction image, because in principle you're looking at an intersection of a sphere with a linear reciprocal lattice. That's what you have. And of course, if you rotate this whole thing, if you rotate your crystal and you rotate the reciprocal lattice, which usually works a bit smoother, you get different reflections into reflection condition. You can try this again. Same thing, you always move the reciprocal lattice through here, and that's what you see happening on the detector from image to image. So you probe the entire reciprocal lattice with your detector. And what's also in that, in the concept of Bragg's law, is this is actually how we define resolution in crystallography. We don't say a resolution of 2.0 angstroms means that if you have two atoms at 2 angstrom difference, you still get separate maxima. That's actually pretty much what comes out, but the definition of it is this. Your resolution is the smallest distance of lattice planes, which do not exist, that you still record, from which you still record a reflection. Okay? And the distance of lattice planes is smaller the further you go away from the origin here. So the higher resolution reflections are more to the outside of the diffraction image. Well, that was what makes us so happy. Okay. Now if you have that, you have a way of sorting all your reflections into the right HKL indices to run the Fourier transform. And then you need to do this, and this is the only really important formula in crystallography. This is the electron density formula, the electron density function. Okay. That's what we want to do. And what that means, of course, and you all know what a Fourier transform is. A Fourier transform is basically an addition or a representation of any function that you have in real space as an integral, or in this case, as a sum of individual wave functions. So we have wave functions that go into here. Our wave functions are very simple wave functions because, of course, they basically consist of a wavelength, of an amplitude, and a phase angle, but we are using monochromatic X-rays. So all our X-rays have the same wavelength, which means we can pretty much forget about the wavelength. We only have two parameters that count for our wave functions, and these are phase angle and amplitude. So technically, we really have a very simple formula for each one of these waves that we need to add up, that we need to Fourier transform. And in some way, our little black dots, that's all we measured, the intensity of these little black dots must represent this. Okay, now how does that work? Well, this is something that you saw already from Nikolai yesterday. We're representing our waves as complex numbers. How are we doing that? Well, we're looking at the Gaussian plane. This is an Argon diagram, and the complex number in the Gaussian plane would be one with coordinates on the real axis and on the imaginary axis, something like this. And of course, you could represent it by a positional vector in the Argon diagram that has a length, which is absolute value of f, and that has an angle with the real axis that we call the phase angle. Then, of course, you can calculate these sides. That goes on very easily, and that is how we represent a wave. Okay, where's the wave? The wave is in the fact that, of course, this one has an additional component that's not drawn in this picture, and that's the component of time. Over time, this vector changes, and it changes in a way that it rotates. So the time axis would be coming out of the of this slide towards you. And over time, this vector will rotate. And if you then look at the projection on the real and the imaginary axis, of course, you get cosine and sine functions according to Euler's formula, which is this complex exponential function that we're working with. So this is our representation of waves. And the nice thing about this is we have monochromatic X-rays. I keep repeating myself. That means we have the same frequency. All those individual waves that we need to add up all rotate at the same speed. And that means we can totally forget about the rotation, right? Because all the individual waves can be represented by individual vectors with a length and an angle to the real axis. And the fact that their wave character is actually a rotation over time doesn't play any role. If we want to do maths with these waves, we just do simple vector additions here at this point. And this is called the structure factor. That is our representation in Fourier space. That is the wave function we need to add up. And this wave function can be measured from the intensity of our black spots. That's almost, so we're almost there. That's just this here, intensity of the black spots. Okay. The problem is, this is a complex number. And what we are measuring, the intensity, is the square of the amplitude, or it's actually the square of the structure factor if you want. But if you square a complex number, then it's, in fact, it means you multiply it with its complex conjugate. That's the complex conjugate. And multiplying these guys invariably gives you a real number, which means measuring things this way makes you lose the phase angle. You cannot measure the phase angle. All we measure is intensities, which is the square of the amplitude, but we don't get information about the phase angle, and that is a bit of a problem. That's what's called the phase problem of crystallography. Which means this is our little black spots, and that's the other part that we miss, and we can't really measure it. Okay, how do we get this? Well, the way we get this goes back to these guys, which I only abuse now because I have the right pictures for them. But these are Jerome Karl and Herbert Hauptmann, who got a Nobel Prize, this time for something pretty complicated, actually, which is to solve the phase problem for small molecules. That's why if you do small molecule crystallography, nobody talks about the phase problem. If you have like 100 molecules, you can get over it thanks to those guys. But what I want to point out looking at them is that if you take these pictures, let's take these two-dimensional representations of the structures of Karl and Hauptmann and Fourier transform them. Right? You can do that. So you can basically run a Fourier transform of these pictures. You generate amplitudes and phase angles for both of them, for Jerome Karl and Herbert Hauptmann. And then if the pictures have the same resolution, have the same dimensions, then these phase angles and amplitudes are just columns in a text file. And then you can go and swap those columns. So you can combine the phase angles of Hauptmann with the amplitudes of Karl, and vice versa. And then, of course, you can back transform. And you can see what comes out of those. And what comes out of those is a bit scary. If you, well, no, I mean, they must have been very nice gentlemen, but it's scary if you keep in mind that the phase angles is what we cannot measure. This is a picture with the amplitudes of Hauptmann and the phases of Karl, and this one has the phases of Hauptmann. So the phase information very strongly dominates these pictures. That's where most of your structural information is, and that's what we cannot measure, and that is a pity. So we need solutions to the phase problem. Obviously, there is even a program that's called Phaser, which we use commonly, but we need something of that kind. And there are a few methods that I really only, I might stop here and leave this as the ultimate cliffhanger, but if you give me 5 more minutes, I could, thank you. He was deliberately looking away, but I'm almost done. There are several ways. One is to just steal the phase angles from somewhere else, and the other one, and that is what we want to do in the practicals, and that's why I still need to talk about this briefly, is to make a de novo structure solution. And stealing the phase angle is kind of easy. You have an unknown structure, and you only have the amplitudes measured, and you have a known model. And this known model can be back transformed, because Fourier transform works both ways, into phase angles and amplitudes, and then you just take the phase angles of the model, if it's similar and if it's in the same orientation, and make a first electron density map and see what happens from there. That's molecular replacement, but that's kind of boring because it means that there must be a very similar structure, otherwise it doesn't work. Now in this de novo structure solution, we are not using the electron density map because we don't have phase angles, so we basically square the electron density map, and we get what's called a Patterson function. And in this Patterson function, that is what we can calculate without having phase angles, we can also calculate a Patterson map. And in this Patterson map, well, let's see, in real space, you would have atom positions. And if you go to the Patterson map, you lose the phase information, which is the absolute placement of your individual atoms in space. But what you still get, really, is you get vectors that correspond to distances between those atoms. So you don't get those red vectors, but you get all the distances between those atoms. And the problem is that, of course, because you don't have an absolute origin in that map, you get all these vectors in the origin of your map. So a Patterson map from these 3 vectors would pretty much look like this. That's what you can calculate. And if you happen to have a structure with only 3 atoms, then it probably doesn't take you long to realize that, hey, the picture is actually in here somewhere. It's also here, and it's also here. But it's n² peaks for n atoms. So if you have a protein structure, that's going to be a pretty busy picture, and you're not going to recognize anything anymore because it's also 3-dimensional. So, meaning, if your structure is simple, you can solve it. If it's more complicated, you cannot solve it. And that leads to the key method for ab initio structure determination, which is substructure analysis. If you have a simple enough structure, you can understand what's happening. For proteins, that's not true. But if you made the right choice at some point of your life to go into bioinorganic chemistry, then your proteins have this very nice feature of having a very limited set of atoms that are unique to this protein, and you might only have 3, 4, 5, or 20 of them, but not 2,000 or 20,000, and that's, for example, the metal sites. So if you can identify a subpopulation of atoms in your structure and determine their position, for example, from a Patterson map, then you can use that to solve your entire structure. And that sounds a bit like magic, but that's what we're going to show you in the practicals, where we're going to solve this structure of the ferridoxin I had on the slides very early on by using the positions only of the iron atoms in the end. And I'll just show you this picture, and then I really stop it here. Because what we have is, for every single structure factor, we have the structure factor of protein and heavy atoms. The heavy atoms might be the irons. We don't know that. But because everything is nicely additive in our structure factor pictures here, this means that we have this as a structure factor of the protein plus a structure factor of the heavy atoms, and the heavy atoms have a structure that is simple enough. So what we can do is we can determine not really the structure factor of the protein, but we know its length because we know the little black spots. We have measured the intensities, so it must be somewhere on this circle. Okay? But what we do know is the position of the heavy atoms. That means for the heavy atoms we have the vector in whole, we have its length and we have its orientation. So for the heavy atoms we know both, and we can actually draw this vector. And because of this triangle that I showed you before, we can say if all of this goes together for FPH, then we might as well draw the FPH circle, for which we also don't have a phase angle up here. And if we do that, then basically there is only two possible solutions, unfortunately. But there is two possible solutions for this triangle that I showed you before. So either that or that must be the right phase angle. And to get over that, we need some additional phase information, which I'm not going to go into detail, but that's the basic idea. That is why only knowing this little arrow of metal sites that don't even have to be part of your metalloprotein, you can make a thallium or mercury or whatever soak of your structure and determine these atom positions. And if you have those, they actually help you to get this phase triangle completely, and then you have the phase angle and the structure. And that is basically the end of structure solution at that point. And this is pretty much where we're going to pick up in the practical. So we're starting with the diffraction image, and then you're going to go through the entire process of processing this data, identifying the position of the iron atoms, and then solving a structure, and then, if you want, go into model building, because all you get is the electron density map. There is no model in, and that, again, is interpretation. Okay, so I guess I'd stop here, tell you the rest in 2 years, and happy to take your questions at any time. So I'll be around if you have any further questions or you want to get the rest of the lecture in private, just find me. Thank you very much for your attention.